Now see, one more case is left. How to calculate entropy in adiabatic processes. So I am taking first adiabatic reversible. So as all of we are knowing that in adiabatic process delta Q is equal to 0. So delta Q is equal to 0 means there is no heat change between system and surrounding. So definitely delta S of surrounding reversible, this is equal to 0. One thing is clear. Why this is 0? Because there is no heat transferred between system and surrounding, right? So means surrounding is not in the contact with our system. So whatsoever entropy is changing here in adiabatic process, that is basically the entropy change of system only. That is not the part of surrounding, right? Surrounding will not, contribute or interfere in any way in adiabatic process. Now, what about system? So suppose that gas is expanding here. I am taking one example of this. So expansion or compression. So all of you are knowing that in expansion and compression, all three variables are changing except n. Number of moles are constant. Rest T, P, V all are changing. So entropy change of system is equal to what? N CV ln T2 by T1 plus NR ln V2 by V1. So entropy change of the system is given by this equation. If you analyze this equation, V2 is greater than V1, so due to volume change, right? Due to volume change, entropy is increasing. Means delta S, this is increases. Or you can say delta S is greater than 0. But when V2 is greater than V1, definitely T2 is less than T1. So this time entropy change is negative, and the magnitude of both is equal. So basically delta S, this is 1, this is 2. So delta S of system is equal to 0. See, means what I am trying to say, that here volume increase in volume increases the entropy, and this temperature drop in temperature decreases the entropy, and these two terms exactly cancel to each other, right? So in case of reversible adiabatic expansion, what is the delta S total? So delta S total is equal to delta S system plus delta S surrounding, and this is equal to 0. So you can say this is an iso, and entropic means there is no entropy change. Isoentropic means this O will be dropped. O and E cannot be together. So this is isentropic process. So adiabatic reversible process is known as isentropic process, means there is no change in the entropy, right? Okay, good. Now second case, I am taking B. I am taking adiabatic irreversible process. So if we take irreversible, so adiabatic irreversible process, in case of adiabatic irreversible process, again delta Q is equal to 0, means if delta Q is equal to 0, means surrounding delta S is equal to 0, right? Surrounding entropy change for the surrounding, it is equal to 0. Then what about system? The same formula, as we know that we don't have the different formula for this. So NCV ln T2 by T1 plus NR ln V2 by V1. But this time these two terms were not cancelled to each other. Means you can say delta S system, this is not equal to 0. So delta S total here, is equal to delta S system plus delta S surrounding, and this is equal to non-zero, right? That is greater than 0, right? So this is not isoentropic process. Basically, there is some change in it. Although these two terms try to compensate to each other, but not exactly compensated to each other like this reversible process. Clear? So this is the all the formulas I have given you for the calculation of entropy. So let's do some practice on these formula, how to apply these formula on the questions, right? Well, see, let's do some problems based on all above the formulas which we have discussed here. See, read carefully this problem. A Carnot engine operates between two thermal reservoirs at 100 degrees Celsius and 0 degrees Celsius. What amount of work can it produce for each 1000 joules of heat absorbed from the warm reservoir? So I think I have given you the direct formula for this. First, from the first information, 100 degrees Celsius and 0 degrees Celsius, first you have to calculate efficiency for this cycle, and by using that efficiency data, you can calculate work, right? So, see, efficiency of this Carnot engine, efficiency Carnot is equal to, you can write TH minus TC by TH into 100. TH is the warmer reservoir, this is colder reservoir, heat reservoir, and this is the TH. And this we have written in the formula. If you refer your notebook, this is 1 minus T1 by T2. T2 by T1, where T2 is the cold and T1 is the hot there. So here I have changed the notation TH, TC, so it becomes clear. So TH is 373, yes, 373.15 minus 273.15 divided by 373.15 into 100. So this is equal to, you can write here, solve this, and what is the value? 26.8%. 26.8%, right? So from the first information, this information 100 degrees Celsius and 0 degrees Celsius, we have calculated the efficiency for that Carnot engine. Now work, amount of work. So W work is equal to minus of efficiency into heat supply. This equation, as you know, efficiency is equal to minus of work by heat absorbed. So total heat, this Q is the heat absorbed from the hot reservoir, right? So it is given what work can it produce for each 1000 joules of heat absorbed from the warm reservoir. See, warm reservoir it is given. So you can write here minus 26.8 multiplied by 1000 divided by 100, because this is 26.8%, right? So this is equal to minus 268 joules. So this is the work delivered to the surrounding work delivered to the surrounding from that heat engine, right? So this is the simple explanation of this. Now come to the next question. See, first all of you should read this question and then we can solve this. A Carnot engine is to operate with at least 15% of efficiency rating. Okay, 15% efficiency rating. The warm heat reservoir will be boiling water at 100 degrees Celsius, and the cold heat reservoir, see, cool heat reservoir will be the cool water, means it is not given here, temperature of this is not given, so let it be Tc and this is Th. What is the maximum temperature of the cooling water that will keep the efficiency rating above 15%, right? Above 15%. So here in this question, we are not supposed to do the calculation in equality manner. We have to calculate in inequality manner, right? So let's proceed. Answer. So efficiency is 15%. 15%. So 15 by 100. So Carnot engine operate with at least 15% efficiency. So this is 15%. Lesser sign here will become and here Th minus Tc by Th. This you can use, right? So by using this you can calculate Th is 373 Kelvin minus Tc, sorry, this is Th not Tc. This is Th, right? Tc by 373, right? So solve this equation, and after solving you will get the correct answer, right? So how to see, this is 15 by 100, 15 into 373, okay, is equal to this divided by 100 is equal to 55.95. So we can write here 55.95. It is less than 373 minus Tc, right? So you can write here Tc, temperature of cold reservoir, that should be greater than 317 Kelvin, right? And this is equal to 44 degrees Celsius. So this we can write here Tc. I mean, this minus this is equal to minus of this Tc. What we can write here? 55.95 minus 373. It is less than minus of Tc. So you can write here Tc is equal to Tc is greater than 317, right? So what you can do here, you can multiply this with minus sign, so this becomes positive. So this Tc should be greater than what this is minus, this is plus, so this will come 317 Kelvin. Okay, so in this way you can calculate. So temperature of that cold reservoir should be greater than any temperature. You can take greater than 44 degrees Celsius, right? But not less than 44 degrees Celsius. If your temperature of cold reservoir is less, then efficiency will be less than what this 15%, right? So the minimum efficiency, this should be maintained at this 15% when Tc is greater than this. Okay, now come to the next question. See, a Carnot engine operates between two thermal reservoirs, 100 degrees Celsius and 0 degrees Celsius. Okay, 100 degrees Celsius and 0 degrees Celsius. During the operation of the engine, 25% of the work produced is dissipated by the friction. How much heat must the warm reservoir supply to engine to produce 1000 joules of useful work? So see, this is also a very simple question. First, you have to calculate W total. So W total is equal to W useful plus W friction, loss due to the friction, right? W friction. So this is equal to, you can write here 1000 joules. See what is given. How much heat must be? How much heat must the warm reservoir supply to engine to produce 1000 joules of useful work? Right, 1000 joules of useful work. So the total work is equal to useful plus this friction. And what is this value? Friction, W friction. W friction is 0.25, 25%. 0.25 of W total. See. So total, actually this 0.25 of W total, this is dissipated. So if we add this amount of work in the actual output of the work what we needed, then we can calculate the amount of heat energy required to produce such work. So from here we can calculate W total minus 0.25 W total is equal to 1000 joules. So from here we can write 0.75 W total is equal to 1000 by 0.75 joules. So total heat energy, total work 1000 divided by 0.75. So this is 1333. 1333 joules. 0.3 joules, right? So this much heat energy is required to deliver effectively 1000 joules of useful work, because this 0.25 is wastage. So I have added this 0.25 wastage work here in the useful, so that this amount of heat energy is total required here, right? Now W total we have. So what is asked here? How much heat? And thermal reservoir is it is given. So we have to calculate what this efficiency. So efficiency is equal to, we can write efficiency is equal to TH minus TC by TH into 100 is equal to, we can write total work output divided by heat input, or QH, we can say, into 100, right? So this we can I will put here. So this is 373.15 minus 273.15 by 373.15 into 100 is equal to this 1333.3 by QH into 100. So solve this. So this is cancelled, and 100 by 373.15.26. So QH is equal to 1333.3 divided by 0.2679. $4976. So if you take 4976, joules of heat, if you withdraw this heat from hot reservoir, so this will do the work corresponding to the 133.3 joules, out of which 1000 joule is what useful, and rest is lost during the friction, not during friction, in the friction. Now see the next question. Calculate the following, means calculate the delta S system, delta S surrounding, and delta S total for reversible cooling of an ideal gas monoatomic from 298 Kelvin to 273 Kelvin under constant volume. So see, I am taking first part. So constant volume. So dV is equal to 0. So if volume is constant, means there is no change in entropy due to the volume change. So your formula for system, as all of you are knowing, the process is reversible. One more important thing is the process is reversible, right? So delta S system is equal to N CV ln T2 by T1, right? So by using this formula, simply you can calculate the entropy change of system, right? T1 is 298 Kelvin, 298 Kelvin, and T2 is 273 Kelvin, right? Okay, so N is equal to how many moles? So moles are not given, so you should take one mole. Don't take from your side, or I can put one mole of an ideal gas. Cooling off, one mole of an ideal gas. I can take one mole of an ideal gas, right? So one mole and CV is equal to what? For monoatomic, CV is equal to 3 by 2 R. So this is 3 by 2 R means 8.314 joules per mole per degree Kelvin, and into 2.303 log T2 is 273 and T1 is 298. So see, this moles per mole, it is cancelled. So joules per Kelvin, this is the unit of entropy. So if you solve this, after solving this, you will have the answer is minus 1.09 joules per Kelvin, right? This is answer. So this is delta S of system. So what is the delta S of surrounding? Delta S of surrounding, this is equal to positive 1.09 joules per Kelvin. And what is delta S total? This is B, this is A, and the C is delta S total is equal to 0, right? Because this is a reversible process, so this is always equal to 0. Now, second part is at constant pressure. At constant pressure. So, at constant pressure, now delta S system is equal to delta S system is equal to your formula is like this: T1 to T2 Cp dt by T, right, minus T1 to T2 del V by del T at constant P dt, right? So this term is what? 0. This term is 0 because the dp is what? 0. So your formula becomes like this: NCP ln T2 by T1, and T2 and T1 are same. So here Cp is equal to, the value of Cp will change this time. Cp is equal to 5 by 2 R for monoatomic, So 1 mole into 5 by 2 into 8.314 joules per mole per degree Kelvin, and into 2.303 log T2 is 273. Yes, 273 by 298. So when you solve this, you will get the answer minus of 1.8 joules per Kelvin. So see, the entropy change this time, it is more than the previous case, constant volume case. So obviously this is very much justified, because when you see in your energy system, you have to provide more energy to the system to raise the temperature by 1 degree under constant pressure condition. So obviously, if you are putting more energy to the system, randomness will be more. So obviously, if it is asked that everything is same, gas is same, initial temperature, final temperature is same, and one gas is heated or cooled under constant volume condition and constant pressure condition, then in which case you will have more entropy change. So obviously, whether it is increase or decrease under constant pressure condition, it will have more entropy change compared to the constant volume condition, right? So delta S system is equal to minus 1.82 joules per Kelvin. So delta S surrounding is equal to plus joules per Kelvin, and delta S total is equal to 0. So this is the answer for this question, right? Good. Now, see another question. This is a very interesting question and a good question as well. See, a 25 gram of water at 25 degrees Celsius was mixed reversibly and adiabatically, means there is no heat loss during this mixing process to the surrounding, basically, right? With 75 gram of water sample at 75 degrees Celsius. So I have shown here, this is cold, with respect to this, and this is hot with respect to this. This is 25 gram, this is 75 gram. So when they were mixed, so this is the initial state of our system, and this is the final state of our system. So if we are able to calculate this T mixture, then we can calculate the entropy change for this, entropy change for this, and the total entropy change we can add directly. See, in the question it is asked, calculate the entropy change for each water sample, means for this, and for the combined system, right? So if you add these two, so you will get the final result. So we can we can calculate the final temperature by using this concept. See, this is a lower temperature object, this is a higher temperature object, so this will lose the heat and this will gain the heat. So heat gain is equal to heat loss. Heat lost. Calorimetry principle you can use here. See, 25 gram mass is given, so 25 gram water, so this is 1 by 18 grams per mole, so this is the moles of water multiplied by N. C is given 75.3 joules per Kelvin per mole, joules per Kelvin per mole, and delta T, see, NCP delta T for this, and here N dash CP same and delta T, right? So here this will gain the temperature because this is low temperature. So here delta T is the T final or T mixture minus 298. 25 means 298. This is equal to heat loss. So heat loss means you should put here negative charge, negative sign, and this is 75 grams. So 75 gram divided by 18 grams per mole, into C is the same 75.3, 75.3 joules per Kelvin per mole, and delta T is the T mixture minus it is 348, 348.3, right? This is 298.2 or 15 whatsoever. 348, it is okay, right? So see, this grams cancel, and this per mole, and this is what, mole cancel, grams, moles, per mole cancel, and see, this is 18 cancel, this is also cancelled, and 25, 3. Okay, so what is left here? T mixture minus 298 here in the left hand side, and joules cancel, per Kelvin cancel, right? So T mixture minus 298 is equal to minus 3T mixture minus 3 into 348. So we can write here T 3T 4T mixture is equal to minus 10 minus so this is plus 1044 minus 298. So 1044 minus 298 is equal to 746 divided by 4. So it is 186. So it is 348 1044 and the plus 298 is equal to 1342 divided by 4. So this is 335. So T mixture is equal to 335 Kelvin. So one task now it is complete. Okay. So first we have calculated the final temperature of this mixer. T mixer now we have. Now we can calculate the delta S system for hot water. This is equal to what formula we can use? NCP ln T2 by T1. So NCP ln T2 by T1. So this is equal to uh, NCP ln T mixture. This is the final state T2, and initial state is what? 343. Hot one is this. So 343, 75 degrees Celsius, right? So this is equal to 75 divided by 18. This is moles into what Cp is given here, 75.3 joules per Kelvin per mole into 2.303 log T mixture. We have calculated 335 divided by 348. 335 by 348. And now if you solve this, you will have minus 11.46 joules per Kelvin, right? Joules per Kelvin. This moles cancel, so you will have the unit joules per Kelvin, right? Now similarly you can calculate delta S system per cold. So this is equal to 25 by 18 moles into 75.3 joules per Kelvin per mole into 2.303 log 335 by 298. So for this we have 12.38 joules per Kelvin, right? Now delta S total system, or delta S combined, we can say, not total, because here we have not calculated the surrounding. Combined is equal to delta S hot plus delta S cold. So this is equal to hot, we have minus 11.46 and this is plus 12.38. So this is equal to what? 0.92 joules per Kelvin. So this is the answer. Right? So in this way you can calculate the entropy change in the for the combined system and for the individual system, right? Now see another question, but there is some link with the previous question here. So read the question carefully. Calculate the delta S surrounding for the process described in the above question, assuming that both samples transfer heat to a heat reservoir 335 Kelvin. So this description I have shown here. See, this is our system, this is another system, and this heat reservoir is common for both. It is at 335 Kelvin, right? This time these two are not mixed together, so we have to find out the entropy change of this, right? So first, if you are able to find out what is the heat change for this cold and for this hot, so heat change of this surrounding, so Q of surrounding cold first. Cold means this 25 degrees Celsius. So this is equal to minus 25, or first we have to write formula NCP delta T, right? So what will be the final temperature of this? Obviously the final temperature, if it is in the contact with the hot reservoir, after some time the temperature will be finally adjusted at thermal equilibrium. So this is minus N is 25 by 18 moles multiplied by 75 point what 3 joules per Kelvin per mole, and T final is finally this will come 335 minus 298 Kelvin, right? Okay. So what we get from here, we will get minus 3919 joules. So this amount of heat energy transferred from surrounding to system, this side, because see, this is negative for this surrounding, right? We are calculating Q of surrounding of this, and similarly Q surrounding for hot, Q surrounding for hot. So this we can write minus 75 by 18 moles multiplied by 75.3 joules per Kelvin per mole, and this time 335 minus 348 Kelvin. So if you solve this, you will get 3919 joules. So this value is coming positive, means what is happening? This amount of heat energy is transferred from this hotter system to here in the hot reservoir. But you know, due to the transfer of this heat or due to the attraction of this heat, you cannot change the temperature of this. But now you have calculated that this amount of heat is transferred from surrounding to system of cold, and this amount of heat energy transferred from system of hot to the reservoir. Right now we can calculate delta S surrounding for the cold. Delta S surrounding for the cold, this is minus 3919 joules divided by T, that is constant 335, right? So this is equal to minus 11.67 joules per Kelvin. So if we want to calculate the delta S universe for this cold, delta S total for this cold is equal to 12.38 joules per Kelvin. This is system. It is we have calculated here in 12.38 delta S of system we have calculated in this question, plus this minus 11.67 joules per Kelvin, right? So this is equal to minus of 0.7 joules per Kelvin, right? So this is for delta S surrounding for cold and delta S total for cold. Total means system plus surrounding, or you can say this is universe. Not this time total. You can write here universe. Similarly, we can calculate for the hot. So delta S surrounding for hot. Surrounding for hot, this is equal to 3919 divided by 335. So this is 11.67, the same 11.67 joules per Kelvin. So this is this amount of heat energy is added to the surrounding, and this is the temperature of the surrounding. So this is the entropy change of the surrounding with respect to the hot system. Now delta S universe with respect to hot is equal to, what is the system we have calculated for hot, minus 11.46 plus 11.67, right? So this is equal to 0.21 joules per Kelvin, right? So for the complete process, we can write delta S surrounding is equal to complete. So this is equal to delta S surrounding cold plus delta S surrounding hot. So this is equal to minus 11.67 and plus 11.67. So this is equal to 0, right? Because you know the surrounding for both the surrounding is same, and same heat is from one side it is coming and from other side it is going. So obviously there is no change of the entropy in the complete whole process, whole system. Similarly, you can you can calculate the delta S universe for this hot and this cold. So if you add this 0.71 and 0.21, so definitely this should be equal to 0.9, right? So you can add this delta S universe is equal to delta S universe. Although it is not asked in this question, but I am calculating this cold plus delta S universe. This is the problem, dear students. That's why we need another function, because until or unless we do not have the idea about the system and surrounding both, we cannot make it for spontaneous process. So for cold, it is 0.71 we have calculated, plus for hot it is 0.21. So this is equal to 0.92 joules per Kelvin. So if sometime directly asked that what is the delta S surrounding total, so obviously the process is reversible. So directly you can show that the same entropy will change for the what surrounding also, right? So see, this is the calculations. This type of questions may be asked, right? Now see one more question. This is a very simple question. This is based on the entropy of mixing. So, what is the entropy change for the system producing one mole? So, N total is equal to N is equal to 1 mole, it is given, of air consisting 79% of nitrogen. So, this volume fraction you can take the mole fraction. So, mole fraction of nitrogen is equal to 0.79, and 21% of oxygen means mole fraction of oxygen is equal to 0.21. Now system mixing is equal to minus N into R, X of nitrogen ln X of nitrogen plus X of O2 ln X of O2. Put the value and solve this and get the answer. Minus 1 mole, R is 8.314 joules per mole per degree Kelvin, and this is whole dimensionless. 0.79 ln 0.79 plus 0.21 ln 0.21, right? So if you solve this, you will have total value will come 4.27 joules per Kelvin. This is the answer, right? Now, similarly, one more question it is given. Hydrogen has two isotopes. One H we are considering, and this D. Calculate the entropy change for preparing of molecular hydrogen. So C, H and D, H and D, if you take, so what are the different combinations for the molecule formation of molecules? See the question. Hydrogen has two isotopes. One H1 is this percent and one HD is this percent. Calculate the entropy change for preparing the molecular hydrogen, right? So this is very simple. Total moles we can take one, right? So what are the different possibilities for the molecule formation? This is H2, then H and D, then D and H, and then D and D, right? So the possibility of the formation of this HD or DH, you can say same molecule. So this is twice of the D2 and H2. So mole fraction now you can calculate. Mole fraction of hydrogen H2 molecule is equal to 0. Fraction of this 0.99985 multiplied by 0.99985. So this is equal to 0.99970. Similarly, mole fraction of HD is equal to twice of 0.99985 multiplied by 0.015. 0.015. So this is equal to 3 into 10 power minus 4. Similarly, mole fraction of D2 is equal to 0.00015 multiplied by 0.0015. So this is equal to 2.3 into 10 power minus 8. Now, entropy of this mixing, right, of the system is equal to minus 1 mole total. We can take this is total 1, and R is 8.314 joules per Kelvin, and 0.9997 ln 0.9997 plus 3 into 10 power minus 4 ln 3 into 10 power minus 4 plus 2.3 into 10 power minus 8 ln 2.3 into 10 power minus 8. If you solve this complete equation, so you will get 0.0227, right, joules per Kelvin, and you can write per mole, because for 1 mole we are taking, or we have taken here 1 mole. So joules per Kelvin per mole here, right? So this is cancelled. So joules per Kelvin, right? So this is the entropy change in the formation of these molecules from the atom hydrogen and deuterium, right? So these are the different questions which can be asked to you, and how to solve all these questions I have given you some idea.